So number 10 is a division problem. So of fractions. And another way you could write this, like this is how you're used to seeing division of fractions. You're used to seeing a numerator and a denominator like this. So these representations are exactly the same. And it doesn't matter whether you write it horizontally or vertically. But what do you remember, hopefully, about dividing by a fraction or dividing by any number? This works. Yeah? You flip it. Flip and multiply. Okay. And it's not a term. What is he referring to? What are we flipping? And what's the official word for flipping? Reciprocal. Multiply by the reciprocal of what? The denominator, right? So it's this denominator. We take the reciprocal of this and we multiply it by the numerator. In this case, it's still the denominator. It's not a term. The only way it could be a term is if there's a big fat plus here or a big fat subtraction sign. Then they would be called terms, okay? So we're going to apply our rule for division by any number. We don't use it with whole numbers, but we could. If we divide by 2, we could multiply by a half, which is the reciprocal. We just don't bother because we can divide by 2 pretty easily. So this becomes times x minus 1 over 3x squared plus x. Now, before you multiply, you want to try to reduce your fraction because it's a lot easier to reduce now than if you multiply it all out and get cubes and fourth powers and then try to factor it. So it's really helpful to factor it now. So we have 6x squared times x minus 1, that's our numerator. Okay, and the reason I wrote it right there as a single numerator is I can't factor any of this. 6, I could factor 6 as 2 times 3 if I wanted to represent it as prime factors. X squared is x squared, can't be factored any further. And x minus 1 is a prime factor. You can't factor that any further. So what about this denominator here, x squared minus 1? Can we factor that? Okay, well, how do we factor that? X parentheses x minus 1, like that? Yeah. Does everybody agree with that? X times x minus 1? Okay, we can't do it this way because if we did x times x, we'd certainly get that x squared, right? But x times negative 1 is negative 1x. So this is what we call the difference, because it's subtraction, the difference between two perfect squares, right? X squared is a perfect square and 1 is a perfect square. 1 fools us because 1 times 1 is 1. So anytime we see a binomial like this is what we call it, we can go, oh, those are easy to factor. I put an x and an x, which is the square root of x squared. I put a 1 and a 1, but I must change the signs so that we don't have a middle term, because if we multiply this all out, we'd get 1x, take away 1x, and that gives us 0x in the middle. Okay, so now I'm going to put that on the bottom, x plus 1, x minus 1. And what about factoring this second denominator? Someone want to help us with that? How would we factor that? Yep, Moshe? We can take an x out as a common factor, and what would we have left? No? How many terms do we have here, Moshe? 2 terms. So if we have 2 terms there, we've got to have 2 terms in there. And that's always the tricky part. When your GCF is actually exactly like one of the terms, we forget to put the 1 in there. Okay? It's because you have to be able to multiply this times this and get exactly that. And if we just had 3x, we'd have 3x squared there, right? So that's the tricky. So watch out for that. This can be tricky when your GCF is exactly the same as one of your terms. You've got to remember to replace it with 1, because what you're saying here is 3x squared divided by x would give me a 3x in here, and x divided by x would give me a 1. It's a placeholder, absolutely. All right, so now we've got an x here and we have a 3x plus 1. So now we're happy because our numerator is factored. We're happy, it's completely factored. And our denominator is completely factored into all of its primes. We're very happy campers. Now we can call in the Halloween slasher, okay? But not until then. So now we can call in the Halloween slasher to find our famous foo-foos, which are our fancy forms of 1. Okay? And do we have foo-foos here? Where are they? Yeah, top and bottom, which factors are the same? X minus 1 for sure. So when I write that, I replace it with the number 1 because I can multiply 1 without changing it. Any other factor that you see common to the top and bottom? It's kind of hidden a little bit. Is it 3x? No, because this is inside parentheses, Sam. So unless it's okay, that's a good, because like some people might look at this 3x and think you could reduce it with the 6x squared. But remember, this isn't 3x on the bottom, it's 3x plus 1. So unless you see exactly the same thing on top with parentheses, 3x plus 1, leave it alone. Okay. Alex, what? The x's, see, you have a factor of x here, right? Factor of x. And it's hidden, but you have 2 factors of x up here. So you're going to take this x and take away one of those x's, which just leaves you with 1x in the numerator. So now you're all set. Now it's reduced, and you can say your final answer is 6x in the numerator, and the denominator is x plus 1 times 3x plus 1. And you can leave it like that. You don't have to bother multiplying out the denominator for me, okay? Everybody all set with that? It's fine. It just, the difference, Jennifer, is if you multiply this and for some little reason you made a mistake, right, then I have to take off for it. Whereas if you just leave this, no problem. Sometimes at the back of the book we'll multiply it out, or your answer might, and so you just need to be able to look at this and look at the answer and know that they're the same. But it's fine whichever way you want to do it. Okay, is everybody else happy with whatever they put on the board with the answers that they got and the help that they got from your classmates? Okay, so this is what I'd like you to bring to class every day. Take a note as to where your table is. I won't write tables up there every day. In fact, you can go anywhere. I don't care which board you use. Put your questions up. If you get here early, then one of your classmates will help you. I'll help you if I'm here. It's a great way for you to help each other. Okay, so you all starting now, I had asked you to read section P1 and to be ready to discuss the preview exercises at the beginning of class 2. So that's these exercises right here, 1 through 2, and you have some bulleted questions. I'm going to give you until about 5 past to do that together, and I'll walk around. Put your flags down for now so I know if you need help, your flag will go up. And together you can you can discuss these together. And if you have any questions, let me know. Okay, so what did we come up with for? Let me shut off the music for now. What did we come up with for a few observations of this particular set of data here of the tuitions? Average cost of tuition and fees at 4-year colleges. Just a couple quick observations. And the what? It's definitely increasing between 2000 and 2010. Yeah, Moshe? Okay. Thank you. Yes, from 2003 to 2004, look at that jump in tuition. It's definitely a much bigger jump in tuition than any of these other years. So it'd be interesting if anybody can remember, probably were you all born? Yes, thank goodness. You know, it'd be interesting to think back to what happened in 2003 and 4 that may have caused that increase in tuition and fees. Yeah, Moshe? Okay, doesn't look like it's been affected. Maybe not there, but remember, it may come after, Okay, yeah. Yeah. So it's kind of a very slow growth here, isn't it? And then it, yeah. Yeah. Okay. Okay. I think we're going to look at that in a minute. That's going to maybe be a class exercise. Hey, what does this little kind of squiggly mean in the axes here, in the vertical axis, yeah, Ben? Right, so instead of there being a 0 here, what they did, because if we, and it actually can change how the graph looks visually. That's why you always have to be aware of that. There's no values between 0 and 3,362. So they basically like took a scissor and they cut at 0 and they cut just under 3,000 and they squished it down, right? And so these aren't really tall. I mean, if we started at 0, they'd be so tall, right? So that's right. Yeah. Okay.
You also do it on the x-axis as well.
You can do it on the x-axis as well. They chose not to, which is interesting, but you could have put the little break-in axes there, and I probably would have. But the reason they didn't is because when you see what we're going to be using as a model for this, an algebraic model equation, they're going to have 2000 be represented by the year 0, and that's why they don't have the break there. Okay, so just 2 questions real quick, because I want to start the teaching demo. 2 questions real quick that you might be interested in about the average cost of tuition and fees, given that we're now in 2014, you're all students of higher education. Quick question you might have in your top of your head. Huh? Oh, it's 2015, right. But it would be, if I was doing this graph, would be in 2014, because, but thank you. Thank you, Moshe. I better make sure I know what year I'm in. Yeah, Sam?
Mine was a quick question. So where is this money coming from? And what is that going to?
Yeah, a lot of people have the question. Right.
Heating, electricity, food.
Right.
Where is my money at?
Yeah, where are all these dollars going, right? You want to ask the schools fiscal financial deans those questions. Yep, Marcos? Right. There's a quality increase as well as the tuition and fees. Well, let's hope that, well, I don't have much hope given the Congress that we have, but wouldn't it be great if we had free community college? That'd be fabulous. Yeah, Moshe? Yeah, I mean, if we could ever get free community college, I think it would be great. You know, I think we would hopefully have the same budget or a better budget. Maybe we could even hire more full-time instructors. That would be fabulous. But I don't know. I think I'll be retired before we see that.
Are scholarships included in that graph at all?
No.
Okay.
Well, they could be, no, because this is just straight tuition and fees. All right.
So no financial aid, no
No, no.
Okay.
No, it's just to it. Well, fees would probably include an average, like for a 4-year school, they probably have room and board in there, and they've got, say, an average cost for books and stuff like that, but not money that they then give out. All right, so the answer to this question about when am I ever going to use math, we're going to do it right now. And what we're going to do is we're going to make a model, a mathematical model. So this is the first topic in your section 1.1 that hopefully you read about. And a model is simply a way to represent through mathematics a given situation. And we can do it with graphs, we can do it with equations or formulas, and it will actually try to describe a particular situation in the real world. Okay, so if we try to describe a relationship between 2 or more quantities, we can write an equation relating them. So let's take a look at a model that we're going to use for this particular graph. So I watched one of your fellow students on their paper did something like this. They kind of did a little thing like this, trying to model that. So if we were trying to find an equation that modeled that, one equation you might pick, perhaps, to model this that would be reasonable, I think it would be reasonable, would be to think about trying to find some type of formula for a straight line that might model that. Another type of equation you could use would be to follow what this student was thinking, which, oh, that's only straight, so that's not going to help me. All right, let's get rid of that. So if we look at the green line, that's curved. Okay, so we could probably come up with a couple of different models, and one of the things we're going to work on in this class is how do we determine what's the best model to use for predicting? If we go outside of 2010, right now we would be predicting what the tuition and fees would be based on this equation. If we stay within here, we're estimating, okay? So the model that we picked, the book picked, the author, is this model right here, where T represents the tuition and fees, and X represents the college, the year ending after 2000. So in other words, how many years after 2000? So instead of seeing 2000, 2001, 2002 on the x-axis or your horizontal axis, you would see this 0, 1, 2, 3, all the way up to 10. This is very common when you're creating models where your horizontal variable is years. Those are big numbers to put into your calculator, 2000 or 2015 or 1999. So often you pick a base year, whatever year you want. 2000 is really nice to start with because everything else you're just looking at the last digit or the last two digits. So X is going to be, in this case, a number that's 0 through 10. Or if you go outside of the data set, it will be a number bigger than 10. Or what if we were trying to estimate tuition and fees for a year before 2000? What would our numbers look like for X? They'd be negative, right? So if I was looking at 1998, X would be 2 years before 2000, so it would be -2. Okay? Now, I put this data into my graphing calculator, and I asked my graphing calculator to find a model that really fits this data. And what I mean by fits is it comes really close to the data. The best possible equation I could get is this equation right here. Does anybody recognize what kind of equation this is? Quadratic, right. So they're saying that a quadratic equation, because it has a 2, that's all quadratics. It's a polynomial. Polynomial is the really big class. That's the big class. And this is a special polynomial called a quadratic. So a quadratic equation is the model of choice here, okay? That's what we're choosing to model this tuition based on what year you have, okay? So let's take a look at how we would use this model to find the average cost of tuition and fees in 2010. And you say, why would I want to do that? I got the answer right there. Well, sometimes we want to just see, as a place to start, how well our model actually predicts or estimates. So let's see, 2010, we know that the real tuition and fees is 2010. Let's see what our model would predict. So here's our model, and let's see what I can do now. Did I get that right without seeing it? Is that the right model on your page? Okay. So how would I actually estimate? And when I estimate something based on a model, I want to show you what I do. I put a little hat over it. That's just saying you're estimating or predicting. You use that in statistics a lot. You don't have to do that. Just I want to show you if you see that little hat sometimes, that's what it means. So how would we go about estimating the tuition for the year 2010? What's the value of X going to be here? 10, right? Because it's 10 years after. Here's the year I'm looking at, and I subtract 2000 from it, and I get 10. So where I see X, I put in the number 10 for every X that I see there. Okay, and what do we get? I know some of you have already worked this all out. What did you get? 7,004, right? So this model predicts that the average cost of tuition and fees would be 7,004. We know that the real average cost for that year was 7,020. So it's pretty close, isn't it? It's not bad. So this is what, an underestimate or an overestimate of the real cost? It is an underestimate because 7,004 is less than 7,020, and it underestimates it by how many dollars? $16, right? So it underestimates by $16. Okay. For this model, yes. It's not constant for every year. Every year is different because this is not linear, right? It changes. Okay, so let's use the model to predict the average cost of tuition and fees for 2014, where we are right now, 2014. So how would I do this? What would I do? Does anybody know? Plug in 14 instead of 10, right? Because X is equal to 14. So I want tables 1, 2, and 3 to do this. Tables 1, 2, 3, get the answer for this. In tables 5 and 6, and what would be the value for X for 1990, tables 5 and 6? Negative 10, right? Because 1990 minus 2000 gives me negative 10, right? So you all get the answers, tables 4 and 5. Sorry, there's no 5 and 6. 4 and 5, and tables 1 through 3. And please compare, the tables compare to make sure you all have the correct answer before we put it up here on the screen. If you have a graphing calculator, you can put the model in under the y equals button. I'm interested in checking out some years, right? And I know my years are going to start with a negative number. So I go to my second window, which is my table set. I set my table to be at negative 10. And it's going to increment by 1 if I let the calculator do it automatically. But I'm just interested in checking out 2 years. So I want to ask my calculator to give me the data, the answer for the tuition for just 2 years. So then when I go to my table and I put in negative 10, it gives me the answer. And then I put in 14 and it gives me the answer for that. So it's a real quick way of doing that. Okay, so how do you feel about the prediction for 1990? Does it seem plausible? No, no. We wish it was plausible. That, I mean, it wasn't $184 10 years ago. And so this is why you have to be careful, and you'll hear me say this over and over again. When you go outside of your model to look at data either in the future or the past, your model may not make sense anymore. The data may not follow the same trend of the data that you're actually graphing. So for this model is based on this information. It may not represent what's happening out here. It could increase more rapidly, and it certainly didn't decrease that rapidly. It probably really levels out in the years prior, in the years prior to 2000. It didn't go down. It wasn't as a steep decline as what our model represents. So you always have to be careful when you're using a model. And so what we would say here about this answer, and this is the language you would use, is we would have a model breakdown. That's what it's called. The model's breaking down on either end. Yep.
Then if you do follow the curve, get more of an exponential curve.
There is a difference between the quadratic and the exponential. The exponential is going to grow even much quicker, which is probably what's happening when you read this note. Yeah, when you read this note, you see that the tuition took a huge jump very quickly. So as Sam's saying, it's not even following that model that we have here. It just took this tremendous jump after 2010. So you got to always be careful when you're using a model not to go too far outside your data set. When you go outside the data set, when you use your model to go outside the data set, that's called extrapolation. When you go outside, E-X-T-R-A, extrapolate, okay? When you stay inside your data set and you use it to estimate, like if we did like every other year instead of every year from 2000 to 2010, say we just did the even years and we wanted to use our model to predict the odd years, we'd be inside our data set. So when you're inside your data set, that's called like interstate, interpolation, okay? Interpolation. So you're going to be doing some of this modeling throughout the semester. All right, I'm going to talk for 10 more minutes at the most. We're going to talk about sets and how to represent sets, and then you have a class activity. I think sets, I'm saying sets, not the other word. Sets are, hey, I got a chuckle, yay. Sets, in just simple everyday language, is just a collection of objects, okay? Sometimes we can represent a set by listing all of the individual elements of the set. The objects in a set are called elements. And sometimes we can just list them. Like we could list someone, the the Patriots, the New England Patriots that are going to be playing in the Super Bowl. Who are dressed to play active players in the Super Bowl on Sunday? Does anybody know how many people would be in that set? 40s? Well, on opening day, it's 53. I don't know if they let you have more for the playoffs. I doubt it. So I think a minimum of 53 people would be listed in that set. Okay? That's right, the collection of whatever the elements are. They could be numbers, they could be people, they could be the number of cavities you have, right? Everybody's cavities. Shh. All right. When we can actually list the individual elements, it's called the roster method. Doesn't that make sense? The roster method, because I have a roster right now of everybody in this class, right? The set of students in this class. So if I wanted to represent, often we use capital letters like A or B or C to represent a set. And then what's really critical when you represent a set is to use these little curly cues right here. These are called braces. And so if I was representing the set of the Three Stooges, we would list each name, Larry, Moe, and Curly, and we would put a comma in between. Each element, we'd have a comma. So what I'd like you to do at your seats real fast, 2 points to the table that comes up with it first on their next quiz, which is Wednesday, 2 points. If you can list the set B, which is the 7 dwarfs. Go to it. Quick, 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 quick. What table 3 has here? They have sleepy. They have Doc. They have grumpy. They have sneezy. Oh, they have dopey. Ben, why did you remember dopey? Bashful. And happy. Does everybody agree with these? I don't have them memorized. I don't know. Okay. All right, so table 3, remind me when you have after your quiz next week that you're all going to get 2 points as a bonus. All right. All right, and remind me Monday to tell you about the format for our quiz on Wednesday. We'll talk about it then. Okay, so the very last thing we need to know before we start our class activity for today is about another notation for sets, which is called set builder notation. So you want to read this for me, Ben, number 8? Okay, so we can't list every single number in a set if it's like we're talking about the rational numbers or all real numbers because it's an infinite set. So sometimes we have to use this set builder notation. And to use a set builder notation, notice you start off with your braces. And this is how it reads. To read this, you would say the set, because that's what this tells us, the set of all numbers x, that's what you put in whatever variable you're using, x is very common. This straight up and down line is read as such that x meets some condition or condition. So in other words, if I wanted to say the set of all negative numbers, I would write it this way. This is how I could write this, represent the set of all negative numbers. Because I say it's the set of all numbers x such that x is less than 0. Any number less than 0 is called negative. Okay, so before we move on, could someone help me with set builder notation? Say the set of all non-negative numbers. How would I represent the set of all non-negative numbers? Moshe? Curly brackets x, line. Does everybody agree with that? All yeses? Okay. Okay, or would it be greater than or equal to 0? Moshe is now doing an amendment. Okay, he's doing an amendment to his own answer. What do you think? Is it Greater than 0 or greater than or equal to 0? Yeah, non-negative includes 0. We often leave 0 out. If I wanted to say all positive numbers, then this is fine. If I want to say all non-negative, I got to do greater than or equal to include 0. Yep. You no. X can be in there, right? Mm-hmm. Okay, so you're all set now to start your class activity, which gives you more information about intersections and reunions. This is like my favorite example I've ever come up with about the Beatles. We all still know who the Beatles are, regardless of how old we are. Goes into absolute value, and then you work some more with the model. Okay, so you have the next 24 minutes or 23 minutes to work on this.